In this video, we're going to continue talking about the Poisson process, but take a closer look at this arrival processes of customers, patients, any arrival process that you can think of. And take a look at this arrival process and see where the exponential random variable comes to play. So we have this arrival time, right? So when you have when you're observing an arrival process, let's say customers arriving to a store, for each customer you have an arrival time, or if it's not a customer's arrival or whatever that you're observing, there's an occurrence time for each event, and we call that S of J, arrival time of customer J, right? Or patient J. Or if you think about the arrival of earthquake, right? That's also arrival process, arrival time of earthquake 5, right? That's S of 5. So as an example, S of 2, that is arrival time, and pay attention, this is a time. This is a time of arrival. So the nature of this S is time. Arrival time of the second customer, right? So you're observing the arrival processes, and at some point in time, the first customer arrives, that's S of 1, and then sometime later, S of 2, customer 3, S of 3, and each point in time, we're calling it S of J. In the meantime, we have inter-arrival time. And inter-arrival time is a time between arrivals or occurrences, and we call that with T sub J, or T of J, inter-arrival time of customer J. So if you think about this more carefully, there is a relationship between arrival time and inter-arrival time, right? So if I want to put that again graphically, think about an arrival process. This is time 0, and then maybe here the first customer arrives, right? So at that point in time is S of 1. And then sometime later, second customer arrives, that is S of 2. That point in time is S of 2. And then sometime later is S of 3 when the third customer arrives. In the meantime, we have these inner arrival times. So this is T of 1. This is T of 2. T of 2 is the time that it took for the second customer to arrive since the first customer. And T of 3 is the time that it took since the second customer arrived for the third customer to arrive. So these are inner arrival times. So we have arrival time, inner arrival time, and right there you can see the relationship. First of all, T of 1 is equal to S of 1, right? And you can see that this is T of 1, and the same is S of 1. And then here is T of 2, but S of 2 is here. That is S of 2. Here is T of 3, but S of 3 is this whole time. So the relationship between S and T, arrival time and inner arrival time, is that each inner arrival time, let's say T2, is S of 2 minus S of 1. Arrival time of second customer minus arrival time of the first customer is the inner arrival time between the first and second. So we can put that in more generic format. T of J is S of J minus S of J minus 1. So the first inner arrival time and the arrival time is the same, and from there, each inter-arrival time is a difference between arrival times. So why are we talking about this? The reason that we're talking about this is that this random variable t, inter-arrival time, follows a different distribution. It's a different random variable, and that is an exponential random variable. So the time between arrivals, or inter-arrival time, is an exponential random variable with rate of lambda. This is the same lambda that we had, right? Same as Poisson. So this lambda does not change with J. For each customer, it doesn't change. The average rate of arrival is the same. So the interpretation of the whole thing is, if the number of arrivals within a time frame, right, n of t, is Poisson, then the time between arrivals, or inter-arrival time, is exponential. Basically, t of j is exponential. And this t of j is the time between arrivals, and it follows an exponential distribution. What is an exponential distribution, or random variable? X is an exponential random variable with rate lambda. The only parameter for exponential is lambda. So in Poisson process, we're using the notation of t of j, time between arrivals for customer j. And that follows an exponential with parameter lambda. And because this t of j is inter-arrival time, and I want to emphasize on time, the nature of this t is time, and time, as you know, is a continuous random variable. And the range of that is between 0 to infinity. The time between two customers' arrivals can be 0, which means they arrive at the same time, or it can go all the way to infinity, which means the second customer or the next customer doesn't arrive, where the time between arrivals is infinity. So it can't be any number between those two. So let's say that you want to calculate probabilities. Let's say that you want to calculate that the inter-arrival time between the second customer and the first customer, or actually, if you go back here, T2 is the inter-arrival time between the second customer and the first customer. Let's say you want to calculate the probability of that, I don't know, being less than 30 minutes. How do we calculate that? First of all, this t is continuous, where Poisson was discrete, so pay attention to that. So now, from now on, exponential, which is time between arrivals, is going to be continuous. And there is the probability of t2 being equal to 30 minutes is just equal to 0, because it's a continuous random variable. So we're talking about ranges. Less than 30 minutes, between 30 minutes and 15 minutes, and so on. How do we calculate that probability? Well, using the PDF function of exponential, which, as you can see, is a function of lambda. So the same lambda that we have been dealing with. The CDF, cumulative distribution function of exponential, it's here when x is more than or equal to 0. Well, time between arrival cannot be negative, right? So you can essentially disregard that part. The CDF of exponential, we're always talking about inter-arrival times of 0 or positive, right? The time between two arrivals cannot be negative. So that's the CDF function. The expected value or average of exponential random variable is 1 over lambda. Standard deviation is also 1 over lambda. So to summarize, the number of arrivals within a time frame, n of t, is Poisson, But the time between these arrivals, T of j, is exponential, and that is the relationship. You can always refer to that arrival process for customers coming in, and these are time between arrivals. But n of t is the number of arrivals within the time frame. So we're going to look at some examples to make that more clear.